My name is Anthony Kelly, and today I'm going to do a demonstration of Powervation's auto-control.
This is the demonstration board. It shows the PV3012 auto-control IC. It's a two-phase design. One of the phases can be dropped at lighter loads in order to improve efficiency. The board also includes a load step generator. The load step generator produces pulses on the system that you can see the load step response here. If you want to improve the load step response, the traditional way is to add capacitors. You can see that being done here, and the scope shows that the performance improves. Let's mark that with a cursor so that we can see the performance improvement that's gained by adding lots of capacitors. Let's take those capacitors off now and show what auto-control can do. Auto-control can take the system as it is now, which is not optimized, and by turning on auto-control, you can see that the system automatically optimizes to give you a system response which is even better than was achieved by adding those huge number of capacitors. This is our graphical user interface. You can see that when auto-control is turned on, the plot showing the auto-control value starts responding right away and changes cycle by cycle in order to compensate the system for what is seen. You can see that the value is chosen to be in or around 0.3. Let's zoom in a little bit and take a closer look so that we can see the adaptation happening on a cycle by cycle basis. Let's add more capacitors and let's take them out. And we can see that on the plot of the auto-control function, the system knows right away that those capacitors have been added and that they have been removed. And you can see that here on the corresponding scope image. So let's zoom back out now and let's turn back to a fixed controller. We're now going to demonstrate how efficiency saving techniques such as phase dropping can drastically change the dynamics of the converter that makes them so problematic that you really wouldn't want to apply them in practice with regular linear control. You can see that when a phase is dropped, the performance degrades considerably for the fixed controller, making efficiency saving schemes unattractive in fixed control. On the graphical user interface, we enable auto-control. You can see here on the scope, it shows that the performance is dramatically improved for one-phase operation. And when switching from single phase to dual phase, there is virtually no difference, allowing power system designers to realize the efficiency improvements that you can get from phase adding and dropping. So let's change back to a fixed controller on the graphical user interface, and we're in one phase operation. The question must be asked, why not just allow your fixed controller to always operate this well? Well, the answer is that a fixed controller being tuned as aggressively as this in order to give you this excellent performance in one phase operation is just not suitable in two-phase operation. In fact, the system is even unstable. You can see that when we re-enable auto-control, the instability is taken out of the system right away. Auto-control adjusts cycle by cycle in order to keep the system with guaranteed stability.